Space agency. Studying the seafloor? It sounds backwards until you realize the deepest parts of Earth's ocean are the closest thing we have to alien worlds. Super cold, pitch-black water. Pressures that crush steel. Chemical energy instead of sunlight. If we can learn the rules of life and exploration down there, we'll be ready for oceans on Europa and Enceladus up there. Here are 5 big things NASA and partner teams are hunting for at the deep, and why each one could change everything we think about life and exploration. Number 5. Prove that life can thrive with no sunlight at all. Most life you know depends on sunlight. But deep-sea communities live on chemistry, not light. Around hydrothermal vents, microbes turn hydrogen, methane, and sulfur into food, a process called chemosynthesis. If life needs only rock, water, and the right chemistry, then icy moons with rocky cores and salty oceans might also be alive. By mapping vent fields, sampling microbes, and measuring how these ecosystems build full food webs, worms, crabs, eels, researchers are testing a simple question with enormous stakes. Is sunlight optional for life? If the answer is yes here, it might be yes elsewhere. Number 4. The exact chemical recipe that starts biology. The deep ocean runs natural experiments we can't perform in a lab at full scale. At alkaline vents, minerals split water and make hydrogen. Rocks like olivine react with seawater, serpentinization, to release heat and chemical energy. Metals and pH gradients act like tiny batteries. Teams collect fluids and minerals to track which reactions build complex organics, amino acids, simple lipids, precursors to RNA. The goal is to write a tighter checklist for habitability, salinity limits, pH windows, energy budgets, and the distinct chemical fingerprints life leaves behind. Translate that checklist to a moon. If a lander sniffs the same energy gradients and organics, we'll know where to look and what counts as a true biosignature. Number 3. Under ice playbooks for exploring alien oceans. Many of the best Earth analogs for outer space oceans are beneath Antarctic ice shelves. That environment is dark, cold, nutrient-poor, and hard to reach, just like the underside of Europa's ice. Engineers test under-ice robots here, buoyant rovers that cling to the ice ceiling, slender probes that melt passages through ice, long-range submersibles that navigate by sound when GPS is useless. These tests teach crucial survival skills: autonomous navigation with no radio contact, power management in freezing water, sterile operations that avoid contaminating pristine habitats, and reliable sample handling. Every successful dive under Antarctic ice is a rehearsal for a future craft slipping through an alien ice shell into a black ocean below. Number 2. Smarter senses for life detection. In the deep, you can't rely on sight. You need instruments that can taste and sniff the water in place. Tiny mass spectrometers to weigh molecules. Laser systems that spot organic films on rocks. Electrochemical sensors that read redox energy. Microscopes that image cells without hauling them to the surface and killing them. The teams also practice clean sampling, collecting fluids and chips of rock without adding any trace of ourselves. Get this wrong, and a mission can mistake our contamination for alien biology. Get it right, and a probe in a moon's ocean could test water, recognize true organics, and decide on its own where to investigate next. That is the difference between "we found chemistry" and "we found life." Schnuck 1. Robots that can think and survive on their own. The seafloor is a perfect training ground for autonomous explorers. No satellites, no real-time help. Currents, cliffs, total darkness. NASA-linked teams develop AUVs, autonomous underwater vehicles, that build maps as they swim, dodge hazards, trace chemical trails back to their source, and share data in swarms, so one robot's discovery becomes the group's plan. They learn to launch from a mothership, recharge, and return with samples. Now swap seafloor for Europa's ocean. Light minutes of delay mean no joystick control. The probe must decide which plume to follow, which vent to sample, which pattern looks biological. Training that judgment here, in the harshest parts of Earth's ocean, is how we make first contact safely and confidently elsewhere. More quiet reasons the bottom of the sea matters. Climate truth meter. Deep currents store heat and carbon for centuries. Sampling the abyss improves the models that guide policy on land. Planet factory lessons. The mid-ocean ridge is where most volcanism happens on Earth. Studying how rock, water, and heat trade energy there helps explain how rocky worlds breathe and evolve. New materials and methods. Tools built for crushing pressure and salt water, corrosion-proof housings, pressure-tolerant electronics, soft robotic grippers become the hardware for any hostile ocean on any world. Why this could change everything. If we learn that life flourishes without sunlight, that certain chemistries reliably build complex organics, that robots can navigate black water and choose their targets wisely, then the odds of finding life beyond Earth rise from maybe someday to we know exactly how to look. And even if alien oceans stay quiet, we win at home. Better climate forecasts, safer seafloor tech, cleaner sampling, and a blueprint for exploring the unknown with care. The bottom of our own ocean is not a detour from space, it's the launch pad.